Now, by that definition, you have to understand that there is not one single ergodic theorem, obviously, because as I said, we can define ergodicity in terms of any statistic. It could be the mean, it could be the variance, it could be autocorrelation, autocovariance, whatever statistic you can think of, you can define ergodicity. But of course, it gets complicated as the order of the statistic gets large. So the mean ergodicity is probably the simplest one, both to understand and to derive, let's say. And for instance, ergodicity in autocorrelation is much more complicated and so forth. Um, let's start with a basic example. Take the law of large numbers, which is stated here. The probability that as n goes to infinity, the sample mean of these IID random variables converge to the true mean is 1. This is what we have seen. This is the law of large numbers. Essentially, this is the strong law of large numbers. And in fact, this is an ergodic theorem for the mean of an IID random sequence. Suppose that xi here, x sub I, defines in terms of, well, at the time we had defined this as an IID random sequence, well, an IID sequence of random variables. But essentially, that is the same thing as an IID random sequence, a random process. It's the same thing. So here we have, in fact, an ergodic theorem for the mean of an IID random sequence, right? This is because this states the fact that the mean of this, the sample mean of this IID random sequence really converges to the true mean value. But this is very specific. The process here, x sub I, is IID and it's discrete time. Okay, it's very specific. If your process is not IID, then you cannot use this. So what we want to do is we would like to find ergodic theorems for random processes that are not IID, or which may be continuous time also. Okay, so the question is, can we find such theorems? The first thing you have to observe here, of course, is that any time average for the mean, right? You make an observation in an interval and you take its average. Okay, it's essentially it's a time average. So whatever you observe, it will be, well, your observations are going to be numbers. It's not a function you are observing because it's a measurement. You will see numbers. And when you take the average, you will obtain a value, not a function. It will be constant, it will be fixed. So for any random process that this time average converges to the mean of the random process itself must be independent of time. That is the first observation we can make, right? If your mean value, the true mean, if it depends on time, no luck, you cannot actually estimate it with a time average, because what you will get is not going to be a function of time. You are removing the time dependence by averaging, okay? Therefore, for a time average to be able to converge to the true mean itself must be a constant number. So based on this observation, what we are going to do is we will derive an ergodic theorem for White's stationary processes. Okay, we'll assume the random process is White's stationary, which will entail the constant mean, and therefore we will derive an ergodic theorem for such processes. It will not only be a constant mean random process, it will also be stationary in autocorrelation too. Okay? But before that, I'm going to show you that stationarity by itself does not guarantee ergodicity, because this is a common misconception. And stationary is such a strong property that sometimes people assume if a process is stationary, then it will also be definitely ergodic. That is not the case. Okay, stationarity and ergodicity, they do not guarantee each other. In fact, I don't really know any relationship between them. Okay, one does not guarantee the other. They are very different concepts. While stationarity is well, I'm not arguing that it's a strong property, especially in strict sense, but ergodicity is something else. Okay, so let's see an example, quite a simple one and a typical one. Assume that the random process x of t, a continuous time random process, is defined as being equal to a random variable a for all t. Okay, so whatever value a takes, okay, for all time, x of t will be that value. And we also have the distribution here. It's either +1 or -1 with equal probabilities. Now, you have to see that since the distribution, not even the distribution, since the value does not change with time, okay, well, you have a function of time, but it is constant throughout all time. So you will have to see that this is stationary in the strict sense, right? You observe it at any time. Well, the distribution is exactly the same. 1/2 +1, 1/2 -1. Okay, and the joint distribution is going to be, well, the exact same thing because, well, you are observing the same quantity. And obviously, the mean of this random process is 0 because it is with equal probabilities +or -1. So the mean is 0. Good thing that it is constant. Well, it should be because it's stationary anyway. Okay, so at this point, so far so good. We can maybe, since the mean is constant, maybe we can use a time average to estimate the mean. Let's look at what the time average is. Okay, let's say we observe this from -t up to t, okay, according to wherever you put the origin, assuming that, well, essentially you are observing this for a 2t interval, okay, and then you integrate it. Well, obviously it's a constant, it's a, whatever a is. A could be +1 or -1. Okay, so we can take it out of the integration, a, because it doesn't depend on t, and therefore the 2t, this 1/2t, it cancels out with the integral, and what is left is a itself. So the mean is equal to a. Now a here is random, so whatever value a takes, that will be the true mean of this random process, right? For some observation, because that is the problem. You are not looking at the ensemble here, okay? You are looking at one single observation. That is the problem with ergodicity, okay? You have just one single observation. And the mean of that observation is going to be a. And a here is not 0. We know that. It's either +1 or -1. Whatever the outcome that is, it will appear as your time average. Okay? Then definitely you see this random process is not ergodic, right? It's stationary, and it's stationary in the strict sense, right? The strongest kind of stationarity, but nevertheless, it's not ergodic. So it's a very important point. Stationarity definitely does not guarantee ergodicity.